Hi everyone, today we will look at design equations for bending. Design equation for bending. Design equations for bending. So under this we will draw our section diagram for our section. Consider our section, the section under consideration. Then here we have this section of height. Consider the height of the section. We will consider the effective depth from here up to where the reinforcement extends to. We'll consider our D prime here. We also draw our strain diagram. So our strain diagram. We draw our triangular stress diagram. Then we also draw our rectangular parabolic stress diagram. Here we'll draw this. Then we'll draw the last one, which is our equivalent rectangular stress diagram. So we'll draw this. From here, we label this diagram. We'll term this as H, overall height. This is T, effective depth. D prime, this is our reinforcement in the compression zone. Reinforcement in the tensile zone. Next, we look at this is our strain diagram. So this is steel strain. Then we'll have concrete strain, which is ECC. Then we'll consider this as our stress block with all of this as our stress block. Here we have these are triangular stress block. Here we have this rectangular parabolic. And here we have equivalent rectangular. So here we have this depth as 0.9x from this depth to this depth. We have this as 0.9x. X 0.9x. So here we term this diagram as our strain and stress block diagrams. So the theory of reinforced concrete bending assumes that concrete develops cracks in the region of tensile strains, and after cracking, tensile strains here, after cracking in the region of tensile strain, the tension is carried by the tensile reinforcement. This implies that the plane section remains plane after straining, and hence a linear strain distribution results as shown in the diagram. You can see a strain diagram. The three possibilities in terms of the stress diagrams are as follows. We have our triangular. These are stress diagrams. So the three possibilities are: first one, we call it triangular. Triangular, this is the first possibility. The stress is linearly proportional to the strain. So here we say stress is linearly proportional to the strain. Then for the second condition, we have rectangular parabolic. Rectangular parabolic. In this case, we consider that this represents the design at ultimate limit state, and it is the stress distribution at failure when the compressive strain are within the plastic range. So the third condition we have here is known as the equivalent rectangular, and this is a simplified version of the rectangular parabolic. So we simplify this. This is the rectangular parabolic, so we transform it into an equivalent rectangular stress block. The depth of the rectangle, as you can see, which is S, is equal to 0.9x. So here S, this is equivalent rectangular. So here we say S is equal to 0.9x, where x is equal to, or S is the depth of the neutral axis. We call it depth of the neutral axis. So since there is a compatibility of strains between the reinforcement and the concrete, the strains in the reinforcement can be calculated from the triangular rule. So using a triangular rule here, what we have here, we can establish the strain in concrete or the strain in the reinforcement. So on the tension zone, let's wipe off clean the board so that we can have enough working space. So here we have the strain. It says strain in the tension zone, strain in the steel, which is E. This is the symbol of strain. ST is equivalent to ECC bracket D minus X over X. And for compression, this should be equal to ESE is equal to ECC bracket X minus D prime. So for compression, we have E, ST, SE, SC for compression is equal to ECC bracket X minus D prime over X. Talking about this, talking about the depth of the neutral axis here, considering it as X, is X. So here we can make X the subject of formula, where we have X will be equal to D over 1 plus EST over ECC. How did we arrive at this? From here, we make S the subject of formula. How do we do that? We multiply this by this, so we have EST multiplied by X is equal to, here expand this by this, we have ECC D minus ECCX. So we pick this to this side. As we pick this to this side, we have ESC X plus ECCX is equal to ECCD. So what is common here? We bring our X, ESC plus ECC is equal to ECCD. So divide both sides by ESE plus ECC. Divide both sides by bracket ESE plus ECC close the bracket. So this will go with this. We have X is equal to ECCD over ESC plus ECC. So with this, let's go to this side. We divide all through by ECC so that we can eliminate this to have D alone. So what do? Our X will be equal to ECC over ECC D bracket ESC over ECC plus ECC over ECC. So this divides cancel this. So what will be left here? X will be equal to D over ESC over ECC plus 1. So that's how we arrive at this, because X is still equal to D over 1 plus ESC over ECC. So that's how we arrive at this, where ECC is equal to 0.0035. we call it the concrete strain or ultimate concrete strain. Thus, to ensure yielding of the tension steel at the ultimate limit state, the depth of the neutral axis must not exceed a value of 0.4664 for high yield bars and 0.7460 for mild steel.